Okay, so today we are going to look at a few things to do with our addition reactions. So we're going to start with Markovnikov's rule. Now, Markovnikov's rule basically allows us to work out what the major and minor product would be in an addition reaction in which we are getting two products. So Markovnikov's rule was formulated by Russian chemist Vladimir Markovnikov, and it states that when HX, so that's a hydrohalogen, X is commonly used as a halogen atom, so when HX or HOH is added to a non-symmetrical alkene, the major product is the one in which the hydrogen atom ends up attached to the carbon atom of the double bond, which already has the greater number of hydrogens bonded to it. Okay. So we'll do a little example of this. So we'll look at the reaction between hydrogen bromide and propene. So propene is an unsymmetrical or non-symmetrical alkene. And because we are reacting a hydrogen halide to it, we are going to end up with two products. Right, so if we look at applying Markovnikov's rule, it states that the hydrogen atom ends up attached to the carbon atom of the double bond, which already has the greater number of hydrogens bonded to it. So if we look at propene, we can see that this carbon on the left here already has two hydrogens attached. And this one in the middle has one hydrogen attached. So what that will mean is that the hydrogen will more likely bond to the carbon on the left because it already has two hydrogens attached. Now remember, this isn't a 100% thing. This is just something that it favours, and that's why we get a major and a minor product. We don't get 100% of one of the products. So I'm just going to draw our split reaction arrow so that we can draw the two possible products, which we'll call the Markovnikov product and the anti-Markovnikov product. So for the first one, we'll do the Markovnikov product. So what I'm going to do is I'm going to break that carbon to carbon double bond to begin with, and I'm going to draw in all of the hydrogens that are already present. And then what I'm going to do is I'm going to pop the hydrogen onto the carbon on the left. That's the hydrogen, the carbon that has the most hydrogens already attached. And then I'm going to pop the bromine on the middle. Okay, and that is your major product, which we can also call the Markovnikov product because it's following Markovnikov's rule. And then for our other possibility, which we do still get, 25% of these addition reactions will go to the anti-Markovnikov product. So again, we'll break our carbon to carbon double bond. All of the hydrogens that are already there will remain. And then for this one, we're going to put the hydrogen onto the carbon that has the lower number of hydrogens attached. So that middle carbon, and then that bromine is going to go on to the first carbon there. And that's our minor product. Which we could also call the anti-Markovnikov product. Because it's going against Markovnikov's rule. Okay, so I'll give you guys a little moment just to have some time to copy that in before we move on to start to explain why does Markovnikov's rule work? What's the explanation behind it? What's the chemistry behind why it does what it does? Okay, so let's go on to look at the chemistry behind why we get a major and a minor product. So we are going to explain this using something known as the inductive effect. Okay, so alkyl groups. Now, an alkyl group is a group containing carbon and hydrogen. So some examples of alkyl groups might be like a CH3, a C2H5, a C3H7, things like that. Those are all alkyl groups. And alkyl groups are said to have a positive inductive effect. Now, what that means is that they are electron donating and can push electrons onto a carbocation, which is a positively charged carbon atom, stabilizing it. Okay. Now we'll look at what a carbocation is in just a moment. So carbocations are common intermediates in both electrophilic addition reactions, which we are looking at right now, and in nucleophilic substitution reactions, which we will go on to look at a bit later. And there are three types of carbocation intermediate. We have a primary carbocation, which is one alkyl group attached, a secondary carbocation, which is two alkyl groups attached, and a tertiary carbocation, which is three alkyl groups attached. Okay, and the greater the number of alkyl groups, the more stabilizing the effect is. So what we are going to do is we are going to draw a carbon atom, and we're going to make that a carbocation, which means it's going to get a positive charge on it, like so. And for our primary carbocation, we are going to draw one alkyl group attached and two hydrogens. Now, I am only drawing 3 bonds around the carbon because when a carbon atom forms a carbocation, it loses a bond, essentially. So it loses a shared pair of electrons. So it loses an electron it was sharing with another atom, and it loses its own electron as well, which is why we get the positive charge on the carbon, because it's missing an electron. So it's going to have a positive charge, and it's also missing a bond, which is why we're only putting 3 bonds around it. Now, if we only have one alkyl group attached to our carbocation intermediate, the stabilizing effect is minimal. And what will happen is that intermediate will usually break down and reform the reactant. So that's not very stable. It doesn't mean to say that it won't exist for a short period of time. It can exist for a short period of time, but it is going to be very stable and it is going to break down. If we have a secondary carbocation, we have 2 alkyl groups attached. Now, in fact, what I'm going to do is I'm just going to replace the CH3s with Rs that represent alkyl groups, just to make that a bit more general. So for our secondary carbocation, we're going to pop on 2 alkyl groups. So I've got 2 R groups. So R dash and R dash dash represent any alkyl group. So I've got that wee note at the bottom. Now, those alkyl groups could be the same. They could both be CH3s or they could be different. It doesn't really matter. Now, the stability of a secondary carbocation is quite difficult to predict. It really does depend on which alkyl groups are attached, because some are more stabilizing than others. It's not something that we need to know. We don't need to know which alkyl groups are more stabilizing than others. It's just something that we need to be aware of. So a secondary carbocation is going to be very difficult to predict in terms of stability. And then finally, for a tertiary carbocation, we have 3 alkyl groups attached. And because of those 3 alkyl groups, they are all pushing electrons towards that positively charged carbon, and that kind of almost cancels the effect of having that positive charge, because anything that's got a charge on it is going to want to react, and it's going to want to react very, very quickly. And it's not going to be very fussy about what it reacts with. And that's not really very good in organic chemistry, because we want reactions to be predictable. We want reactions to happen in a way that we are expecting. And if you've got something that's very unstable, then reactions happen in ways that we do not always expect, and that's definitely not what you want. So with our tertiary carbocation, because we've got 3 alkyl groups, it is reasonably stable, because electrons are being pushed towards that positively charged carbon, stabilizing it. Okay. Now, we are going to be looking at carbocations a lot. We'll look at them when we go on to look at mechanisms for addition reactions, which we're going to go on to look at the first of 3 in a minute. And then we will also look at them when we look at mechanisms for nucleophilic substitution reactions. So it's well worth kind of getting familiar with these carbocations and their stability. Okay. Right, so we are now going to go on to look at mechanisms for electrophilic addition reactions of alkenes. Now, the first one that comes up in this booklet is halogenation. We are not going to look at halogenation today. We'll look at halogenation on Thursday, because we've just talked about carbocation intermediates, and halogenation doesn't use a carbocation intermediate. It uses a different intermediate. So what we'll do is we'll skip past halogenation, and we're going to go on to hydrohalogenation. So do make sure that you skip past that page for halogenation in your booklets, or if you're just writing these notes down on like a piece of paper so that you can fill the booklets in once we get back into school and they can be printed off, then just make sure that you leave some space on your paper, or just make sure that you're very clear that we are looking at hydrohalogenation just now. Okay. Now, what I would highly recommend for this is that you don't copy anything down as I write it, and just kind of follow on with what I'm doing, and then I'll give you some time to copy it down. Okay. So hydrohalogenation reactions will produce 1 product with symmetrical alkenes and 2 products with non-symmetrical alkenes. And the mechanism for the hydrohalogenation is a two-step process and proceeds via a carbocation intermediate. So what I'm going to do is I'm going to draw out an alkene and a hydrohalogen, and we are going to look at the mechanism for how we get our carbocation intermediate, because ultimately what we do in step 1 is we generate the carbocation intermediate. So I'm going to draw this out, and then I'm going to go back and put in little coloured dots showing electrons so that we can see how the electrons are moving, and then I'll get you to copy it in. Okay, so I'm going to look at the reaction between 2-methylpropene and hydrogen fluoride. Okay, so what will happen is, because hydrogen fluoride is a polar molecule, and that is the absolutely critical part here, because hydrogen fluoride is a polar molecule, the hydrogen atom will have a slightly positive charge and the fluorine atom will have a slightly negative charge. Now, what this does is it creates a positive charge that our nucleophile, which is the alkene, can attack. Okay, so if we remember, in alkenes there is an area of electron density around the double bond that makes it act like a nucleophile, and nucleophiles like to attack things which are positively or slightly positively charged. So what will happen is our nucleophile, the electrons in the pi bond, they will attack the delta positively charged hydrogen, forming a bond between one of the carbon atoms of the double bond and the hydrogen. Now, in terms of this reaction, it can actually go in two ways. We can have the bond between the carbon and the hydrogen forming here, or we can have the bond between the carbon and the hydrogen forming there. Now, what I'm going to do is I'll draw them both, and then we'll look at which one is going to be the most likely by thinking about Markovnikov's rule and by looking at the stability of the carbocation intermediate that's formed. So I'm going to take my curly arrow. I'm starting the curly arrow at the carbon-to-carbon double bond because that's where the electrons are currently. And then I'm going to finish the arrow where the electrons are going to end up, which is the bond between the carbon and the hydrogen. So again, I'm going to split my arrow into two so that we can appreciate the two possibilities here. So back to what I'll actually do. I'm just going to move this slightly closer to the alkene, and we'll pop our arrow there. Just makes it look a wee bit tidier. So again, I'm going to come back and I'm going to color code this to just try to make it a wee bit more obvious where the electrons are moving from and moving to. So at the moment it's kind of all in red, but I am going to come back and go over some of it. So what will happen is we'll form a new bond between the carbon on the left and the hydrogen. In fact, that would be a blue hydrogen, so I will actually pop that hydrogen in blue. Like that. And what it does is, because our carbon atom in the middle has lost the electron, or one of the electrons that put into that double bond, it ends up with a positive charge, and that's our carbocation intermediate. And if we look at that carbocation intermediate, it's attached to 1, 2, 3 alkyl groups. So that means that that's going to be a reasonably stable. So that's a stable carbocation. So that would exist for long enough for another reaction to take place with the carbocation. The other option would be that the curly arrow would go kind of in the other direction, and the bond would form between the hydrogen and the carbon in the middle. So if I pop that in, and that leaves us with our carbocation as the carbon on the left there. Now, if we look at that carbocation, it's got one quite large alkyl group attached to it. So it's got that kind of, it's got 3 carbons and 7 hydrogens attached to it. So it's quite a large alkyl group. However, it's only one alkyl group. So it's going to be pretty unstable. So what we've got here is an unstable carbocation. So what would usually happen is our unstable carbocation would usually form the alkene again. So essentially this hydrogen will kind of be knocked off and will reform the double bond in between the 2 carbon atoms. So that's kind of what's going to happen there. So let's have a wee look at this in terms of the electrons moving, and then I'll let you guys copy it in. Okay, so what I'm doing is I'm popping the electrons that are in the hydrogen to fluorine bond in that bond. Now, because the fluorine has the greater electronegativity value, it is going to pull the electrons closer to it, which gives you your positively charged carbon. So what we're going to do is we're going to draw in, we're going to actually make the carbon to carbon double bond. I'm going to pop them as being black in colour. And a double bond is 2 shared pairs of electrons. So what I've done is I've drawn 2 pairs of electrons there. So that pair of electrons, one of those pairs of electrons is going to form the bond between the carbon and the hydrogen. So both of those electrons in the bond between the carbon and the hydrogen have come from carbon atoms. Now, what will then happen is fluorine will see an opportunity, whilst the hydrogen is being attacked, the fluorine will see an opportunity to get both of those electrons for itself. So both of the electrons in the hydrogen fluoride bond are going to end up on the fluorine. So that breaks that hydrogen to fluorine bond. And what we will see as our other product is a negatively charged fluorine or fluoride ion with both of the electrons from that HF bond. So it's got its own electron that it donated to the bond, and it's got hydrogen's electron. Okay, so I'll give you a wee moment to kind of process that and to get that copied in. And then we'll go on to look at step 2, which is just finishing off the reaction. So I'll give you a good couple minutes on that. Okay. So what we'll now go on to look at is what happens in step 2. So step 2 is nice and straightforward. Now what we're going to do in step 2 is I'm just going to take the stable carbocation. I'm not going to look at the unstable carbocation, so I'm just going to take that first one there. Okay. Now if you're asked to draw an addition reaction mechanism in an exam situation, you don't need to do both the stable and the unstable carbocation. You can just look at the one that would be most stable, the one that would follow Markovnikov's rule. I'm just drawing both as an opportunity to kind of look at the stability between them. So let's take our stable carbocation. So what will happen here is you've got a negatively charged fluoride ion and a positively charged carbocation. So what's going to happen is the fluoride ion will attack the positively charged carbon and will form a bond in between the carbon and the fluorine. So let's look at how that's going to work. So I'm going to bring my fluoride ion here, and what will happen is the lone pair of electrons, or one of the lone pairs of electrons on the fluoride ion, will attack the positively charged carbon and will form a bond. Now, do notice, look at where I have started that reaction arrow. I've started it on the lone pair, and look at where it's finishing. I'm not actually pointing the arrow to the carbon. I'm not even pointing the arrow to the positive charge. I'm pointing the arrow to where the bond is going to go, which is where the electrons are going to be. Okay. Now, if we just have a wee look up here, you can see that in this one, I have pointed the electrons directly to the fluorine, and that's because the electrons both went onto the fluorine atom. Okay. Whereas what we've got here is the electrons are going to form a new bond between the carbon and the fluorine. So it takes a bit of getting used to. So when we look at our product, that bond there that I'm forming between the carbon and the fluorine, I'm going to have that as a blue bond because it's the blue electrons from the fluorine that are in that bond. Now again, when you are drawing these in your exam, if you're asked to draw an addition reaction mechanism, you don't need to put those electrons in, you don't need to colour code the bonds or the atoms. I'm just doing this in the hope that it maybe makes slightly more sense, because I know these are quite difficult concepts to kind of deal with. Curly arrows are never easy. All right, so again, I'll give you a wee bit of time to copy that in. Okay, so that is all we are going to look at today. So we've looked at Markovnikov's rule, which helps us predict what the major and minor product are going to be. We've looked at the inductive effect, which helps us explain why the major product is the major product and the minor product is the minor product. And we've now looked at the first of 3 addition reaction mechanisms. So on Thursday's lesson, we will look at the other 2 addition reaction mechanisms, and unfortunately they are not the same as this one here. One of them has some similarities and one of them is completely different. So we will have to have a little look at those as well. So for the kind of time you've got remaining today, just have a wee look over these notes, have a wee look at this addition reaction mechanism, and just make sure that you're quite comfortable with sort of everything that's going on, and just have a wee check to make sure that your curly arrows are kind of starting in the right place and ending up in the right place, and that you are kind of comfortable with that. What you could even do is just take another alkene. You could take any alkene at all, and you could just say, right, okay, well, if I was to add hydrogen bromide to this, what would my mechanism look like? And just try and draw a wee mechanism for yourselves. If you do draw a mechanism for another addition reaction and you want to know if it's correct, you can just email it to me and I'll look at it and let you know if it's right or not. Okay, so as soon as you're finished copying this out, then you are free to leave.